So let's talk about Quadrature Amplitude Modulation, or QAM. This is probably the most popular type of modulation for higher order modulation. And so an effective solution for increasing the bandwidth efficiency is to combine both an amplitude and a phase modulation. And what I've done is I've shown you an example of 16 QAM here, where here's the in phase and here's the quadrature. And what you can see is that we've gotten two different values of amplitude, right, for both the in phase and the quadrature. And a way to also think about it is I've got an angle here, I've got an angle here, and I've got an angle here. So you can think about it as a magnitude and an angle, or you can think about it as simply superposition of the I and the Q. And what we're really concerned about when we do these higher order modulations is two aspects. One is the power, and the other one has to do with the noise immunity. And the easiest way to compare different combinations of amplitudes and phases is to look at this constellation diagram like I've shown you. And I'll show you an example here. We can do many different constellations. The key things, as I mentioned, is the minimum distance between symbols. And so that's shown here in the red. And once again, that's because as I get noise on this point and noise on that point, the more noise I have, the closer they'll come to one another. So if these two are far apart, I can have a lot more noise and still detect my signals. And the other one is the power. And basically the maximum distance, this blue line, is the power of your signal. And the way to think about that simply is, at this point, I have the highest I and the highest Q amplitude. So I have the highest I power and the highest Q power. And as I go further out, these are going to have higher amplitudes of both, and therefore the overall power is going to be larger. And there's some other constraints that we may need to look at for the generation of I and Qs that may make some constellations preferred over the others. And a good way to kind of summarize this and understand it is to look at the contrast between 16 PSK, or phase shift key, and 16 QAM. And the key differences you can see here are that while you could set this up for the same distance, so let's say that red is the same distance. And if you're saying, well, how would I do that? Well, it's pretty simple. I can just make this circle bigger and bigger and bigger, right? Until this distance exactly equals that distance. And so our noise immunity between the two would be exactly the same. But if you run through the math, it turns out that this amplitude here, to get this separation, is 1.6 dB less power in QAM than it is in 16 PSK. And that basically has to do with the fact that the distance between any 2 points here is the same as in 16 PSK, but the peak to get to the corner is smaller than this peak. So here's a great example where they both have the same bandwidth because we're transmitting at the same period t. Right? They're both transmitting for each one of these 4 bits. They both have the same noise immunity. Okay? However, this requires more power. Okay, so it's clear to see that our constellation choice really does have some trade-offs between the different types. Why might you pick 16 PSK? Let's just do an example. Maybe the hardware that you're building, you can change the phase easily, but you can't change the amplitude. This is actually very true in high frequencies, so tens to maybe 100 gigahertz or more. You want to have your amplifiers always at a fixed amplitude. You never want to have them change amplitude because they become very inefficient. Therefore, it's better just to change the phase. So in those systems, this one, the 16 PSK, would be more attractive. So it's not that one is better than the other, it's just that you need to understand the trade-offs. And at this point, you shouldn't understand all the trade-offs, but you should sort of see the key concepts of noise immunity and of power and of the fact that they're all the same bandwidth. I want to take one final minute to talk about what these constellation diagrams look like. And so down here on the left is a simulated version of a 16 QAM, meaning there's 16 points. And up here, these are actually the, I may not get these, it doesn't matter if they get reversed. So here is your, your quadrature, and the blue is your in phase. And so what this means is that the in phase, which is blue, is going between this value, this value, this value, and this value. And you can see that I've got one value here, one value here, one value here, one value here. They correspond to these values that I just showed. Likewise, the pink has one value, two value, three values, four values, and I've got 1, 2, 3, 4. So the actual waveforms that we look at going into our transmitter have these multi-levels. And if we're to plot each point here, we would get a dot corresponding to each one of these 16 different states. However, as you can see, they transition between, and so oftentimes the cartoons look like this, and we just see the points. But in reality, if you looked on an oscilloscope, you would see it like this, where you're seeing the transition between points, where each one of these is one of the points that we saw over in this diagram here. This is nice and clean because these are square. In the next lab, or the next module, we'll learn a little bit about pulse filtering that actually makes this not square and makes these experimental measurements of the constellations a little harder to read. But you should at least now be able to translate between the pictures you see in the cartoons, what you would see in an oscilloscope, and what the actual I and Q waveforms would look like.